Hi. Here on campus, everyone here. Wow, this room is really full. That's really exciting to see. And those watching live online, welcome to Saturday Morning Physics. I'm Physics Professor Tim Chupp. I'm one of the organizers of Saturday Morning Physics, along with the rest of the Saturday Morning Physics team. And before moving on to our program today, I want to note that Saturday Morning Physics is made possible by you and by your many generous contributions to Saturday Morning Physics. Thanks so much for helping make this sustainable so that we can continue to bring you cutting-edge science topics like today, the intersection of science and policy, like last week's, for those who were here 2 weeks ago, and the intersection, family-friendly events, of which we'll have a couple in the winter term here. We've put together an exciting program, in fact, for the winter term, including talks on robotics, quantum science, public trust in science, which is so important, and the family-friendly events that I mentioned. So, your opportunities to contribute to Saturday Morning Physics Endowment on Giving Tuesday, which is coming up on December 3rd, right after Thanksgiving. What is it about Tuesdays, actually? I don't know. You can contribute any day, of course. So for more about supporting Saturday Morning Physics, please go to SaturdayMorningPhysics.org. Saturday Morning Physics is also grateful to have the support of the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, and the Van Loo Family Endowment, and the Pulakeshi Dayalu Astrophysics Fund, which is supported by a very generous gift from the Dayalu family in providing the support for today's event. And we're honored to have members of the family here joining us. And I'd like to invite Dr. Praveen Dayalu, Clinical Professor of Neurology here at Michigan, to address us on behalf of the family. You need a microphone? Oh, they're down here, hidden. I'm so sorry.
All right. Thank you so much, Tim. Hopefully folks can hear me. Mic's on. Well, I'm so excited to be doing this again on behalf of my whole family. This is the second annual Pulakeshi Dayalu lecture. We're super excited to be celebrating this lecture in astrophysics and are very, very grateful. My sisters and I are so blessed to have been raised by a man, my father, who really delighted in the little things in life, and like, you know, every year after year, Saturday mornings, he would get all prepared, savor his coffee, his breakfast snacks. He would, find himself the best seat, and then as the program got underway, you knew he was actually getting more and more into it. When his feet would start pedaling a little bit. And then he would get all excited, and the speaker would say, "One more thing," and then his legs would kick out, and he would slap his thighs, and he would say, "Ha ha, what a bunch of turkeys." Oh wait, sorry, that was for Saturday morning Three Stooges, which we could also fund in his name if we could, but okay, let me switch notes. Saturday Morning Physics, yeah, so he'd get all prepared, savor his coffee and bagels, chat it up with Carol Raybuck and other retirees here, and then choose the best seat he could find. And as the program got underway, he was getting very excited because his feet would start pedaling a little bit, and then the speaker would say one more thing, and he would bring out his green journal and say, "Amazing stuff." And he would write it down, and he would bring that with him to our next meeting during the week, even if we weren't here, and he would educate lay people around him, friends, family, tennis buddies, about what he learned here. So I think in that spirit, I think my dad would be delighted to know as a speaker that we've got Camille Avestruz, who is not only a pioneer in like really big things like galactic scale cluster stuff, but also little things. And she has a passion for education, for educating lay people like this audience, where we've got a mix of, dentists and librarians and insurance agents and retirees and young people and students. So my dad would be all about this, and I'm so grateful. I will also end by saying, if he was here today, I think what he probably would say is something like, shut the news off, I say. Let's hear about the clusters out there instead. Right. So on behalf of his Earthbound cluster and his wife Nimi and my sisters Rashmi and Archana, his daughters, who are watching in Boston, and his grandkids Raja and Malini, Sheila, and then a number of others in his orbit. I welcome all of you here and all of you viewing online, and love to introduce our speaker. Thank you.
Thank you, Praveen, Dr. Dayalu. And thanks to the family. And I understand that we have people actually online from across the pond, right? Saturday evening physics in India. Very good. Before moving on, and I have a few more details to add about our speaker today. I want to note that today's event, those online can send their email questions to physics@umich.edu. And we've had tremendous question and answer periods after the main presentation, and I expect that to continue today with this fascinating topic. So last year, Fred Adams talked about the formation of the solar system. Today, we're going really big. It's really good to remember that there are things bigger than even the Earth that matter. So I'm honored to add my note of introduction to Professor Camille Avestruz. She's an assistant professor of physics. She grew up in New York City, Manhattan, she tells me, and studied at Barnard College and then at Yale, receiving her PhD in 2015. And she did a postdoc at the University of Chicago and then came here to the University of Michigan as a collegiate fellow in 2019. And in 2021, she became an assistant professor. Her research, of course, is in astrophysics, and she'll tell us all about that today. So I won't go into any more detail other than to say that her research and team work under the wonderful name, and let me read this, the Avestruz Lab for Computational Cosmology and Astrophysics, or ACLCCA. I almost said something else that started with AC. Camille's passion for making STEM accessible to those historically included, as Praveen mentioned, from the sciences and the academy is one of her passions, and I've seen that in action also in her teaching. So today's presentation is just a sample of your engagement and outreach outside the ivory tower of academia, even though we're inside the confines of a lecture hall at the University of Michigan. So without further delay, thanks for joining us and for your presentation, Galaxy Clusters, Special Fields, and Special Challenges. Camille.
Good morning, everyone. Thank you for those lovely introductions, and also thank you for your presence and donation. I'm really excited to be here, and thank you, everyone, for showing up. This is quite an awesome turnout. I gotta say, I was like, whoa, this room filled up. So I will be talking to you about one specific area of the research that I do called galaxy clusters, or clusters of galaxies. And these are very special fields in the sky, which make them pretty awesome, but it also poses some special challenges. So I'll share a little bit about that at the tail end, because that's kind of where the cutting edge of research is. How do we address these challenges to really understand these objects and use them to understand our universe? So I oftentimes like to get to know my audience a little bit. So we're going to start off with just a little bit of introductions. You probably know the people sitting right around you, but if you don't, please introduce yourselves with your name. I'm going to set a quick timer for a minute for you to just get to know one another. If you could share a topic of interest that you have in the universe, whatever it might be. So my example would be galaxy clusters, as you might expect. And just one topic of interest you have outside of science. All right, set a little timer. Just chat with folks next to you. All right, folks, let's come back together. All right. So, any rock climbers or hikers in the room? Just raise your hand. Ooh, I see a handful of hands. Okay, maybe I'll see you around in like parks or at the gym. Sweet. All right. Can I hear something outside of galaxy clusters that folks might have mentioned as an interest in the universe? So it doesn't have to be yours. It could be something that you heard from your neighbor. Black holes. Cool. Any other ones?
Dark skies.
Dark skies. Yeah. One more. What was that?
Technology and aerospace.
Technology? Awesome. Yeah. A lot of technology goes into understanding our universe. Stuff that I wish I knew more about. There's some really awesome things that go into building telescopes. So, all right. What about one other thing outside of science that folks shared? Music. Yeah. What was that? Travel. Yeah. What was that last one?
Flying airplanes.
Flying airplanes. Whoa. All right. Cool. People do awesome stuff in here. Yeah. Okay. Great. So I'll be talking to you about galaxy clusters and structure formation, and part of me getting y'all to sort of introduce yourselves and just get comfortable talking to one another and sharing back is I'll have at least 2 other props for you to chat through some stuff later on. Okay, so galaxy clusters you could think of as key tracers in looking at how our universe forms structure. These are massive objects. They are the most massive gravitationally collapsed structures in our universe. So what I'm showing here is one way in which we can start to understand how structures form in our universe. So it's really difficult, right, to imagine, there's only a certain amount of things that we can really sort of take and measure in the lab. That's stuff that's actually here on Earth. But when we try to understand things that are out in the universe, you can't go over there and weigh things or take the temperature of stuff. But you can simulate things here on Earth and play these games to see, okay, if we add a little bit more mass, add a little bit more of this kind of energy, what happens, right? So I call these numerical experiments. So people ask me, are you a theorist or an experimentation person? And I like to answer, I'm a numerical experimentalist. So yeah, a little bit in between. So what we do to simulate how structure forms in our universe is we essentially create a box that is representative of some subvolume of our universe. We assume some, quote, cosmology, and when I say we assume cosmology, we essentially make some assumptions about the contents of our universe and some key parameters that describe how the universe will evolve over time. So that's an assumed cosmology. We create a box, and we discretize matter, basically create little n, some number of particles that represents all of the matter in the universe. We say, okay, well, these are probably going to gravitationally interact, because we know that that's a thing. We have gravity. We drop a ball, it falls to the ground, so massive things attract other massive things. We assume cosmology, we let gravity run, and we watch something in this pretend box of the universe evolve over time. So the start to, earlier on, a very start to this visualized simulation is when you see that z be very large. So this is supposed to be very long in time. So time runs from here and forward. So I'm going to give you a minute to just take a look from here to when it reaches 0. And I want you to turn to your group of however many folks that you were just chatting with and just come up with a list or some descriptors that describe what changed from the start to the finish. All right, go ahead. All right, let's come back together. I am excited to hear what y'all noticed. All right, so what is something that someone noticed from start to finish? What changed?
Density, yeah.
Density,
And then
yeah.
towards the end, it's like almost Christmas lighting.
Ooh, Christmas lighting, I like that. I like that descriptor. It ends with Christmas lighting. Yeah.
It becomes stringy and slows down.
Ooh, it becomes stringy and flows down. Yeah, I like those descriptors. Any other ones? Yeah.
Coalescing.
Beg your pardon?
Coalescing.
Coalescing.
Like the legs are coalescing along a certain line.
I love that word, coalescing. Yes. Okay, great. I love how people describe this because it's just like, these are not words that I use, but then when I see it, I'm like, yes, that's exactly what it looks like. Cool. All right, so I'll just share some of my own list, and right, it sort of somewhat echoes what you've said, but just to share some of the words that I would use instead, right? So there's some bright spots that become brighter and bigger. This is like a Christmas light thing, right? Like the Christmas lights get brighter and bigger over time, and they coalesce, right? And then something that I tend to notice is not just where the lights are, but where the lights are not. So there's these dark spaces between those bright spots. We call these voids, and they become more visible over time. So those like Christmas light looking things, we call those dark matter halos. I'll say a little bit more about this later because it's like a very weird term. The first time I heard this, I did not start in astro, by the way. I started like just physics. Took very few astro exposure courses. I grew up in New York City, right? So like you can't see the night sky. So I didn't really know too much about the night sky just growing up. And the first time I heard the term dark matter halos was actually when I started grad school, and I just had not a very good image of what that, it just wasn't a clear picture. I'll describe more later. And a side note, so because our universe is expanding, the box that you see at the beginning is actually a fraction of the physical volume of the box at the end, right? So when we're simulating the universe, you might have heard that our universe is expanding at an accelerating rate. This is due to something we just call dark energy because we don't fully understand it. But the volume expands. So as we run a simulation forward in time, we have to keep track of the fact that space is expanding. All right, so how does structure form, like really, right? So this was the start, this was the end. You see like, the coalescing, the Christmas lights, the sort of like condensing and trickling down into these like beadier things as time goes on. How does this happen? So the key thing here is gravitational collapse. Now, there was a demo that we might have been able to show where it's like a bunch of bricks like precariously stacked and just like a little bit of a tip, it just comes collapsing down, and that would have been awesome, except it's really hard to set up, so we won't see that now, but I want you to picture that, right? Like if you have this precarious stack of something like really heavy bricks, right? And you just sort of tilt it over so they're not really quite stacked right. You can just imagine how it just comes crumbling down. Or a deck of cards. I've never done the whole, like, anyone have been able to sort of do the fancy stack of deck of cards? I'm always envious of people who can do that. But essentially, right, because we have gravity here on Earth. Earth is supermassive, like, right? If something is precariously balanced and no longer balanced, it starts collapsing in. So you see earlier on in time, it looked a little bit more sort of like smoothed out, right, homogeneous. And the little tiny bright spots, those are inhomogeneities or little areas where you're going to have an instability where you have a little bit more mass there. And where you have a little bit more mass, it's going to grab a little bit more mass. And the more it grabs a little bit more mass, it grabs even more mass. And so that starts to pull away from the areas that I called voids, right? The blank spaces that you see at the tail end of the simulation. The voids become voidier. So gravitational collapse really drives structure formation. And so when you're collapsing more and more stuff, you start to form what we call halos. So In the sort of yellowish circles, I show some of the brighter spots. These correspond to the more massive halos. The brighter they are, the more stuff there is, right? It's higher density. I remember hearing that word. And the sort of smaller little dots I've circled in magenta, these are less massive collapsed structures or halos. And so the most massive of all of these halos are the ones where we expect galaxy clusters to sit. And the tinier little dots are perhaps where something like galaxy groups or individual galaxies, so our galaxy is a Milky Way, we have a host dark matter halo. So essentially, it's like matter that's blobbed together. That's what a halo is. A halo is not that. This is what I pictured when I first heard this term. I had not taken an astro class yet, but I started in research. I'm like, what is this dark matter halo thing people keep referring to? And I had this image in my head. I'm like, that can't be how structure just collapses. It's not. It's more like this blobby bunch of matter that you see at these knots or these nodes or these Christmas lights of structure along these filaments that kind of flow together. So it's filamentary structure along which matter flows and collapses to form more and more massive halos where we now have things like galaxy clusters residing. Okay. So these mass particles, right, they occupy space. And I brought up, right, our universe is expanding. In fact, it's expanding at an accelerating rate. So if we ask, okay, left versus right, left has less volume but before it's continued to expand. And you might ask, okay, if they differ by how much? And this is something that we quantify and keep track of in the simulation. You can see that there's an evolution of the density of matter, so the energy in the form of matter and the energy density of matter evolves over time. This is one of the things that we make an assumption of when we think of like, let's assume a cosmology, so how things evolve over time. Our universe evolves over time. That is an assumption that we put into the simulation. And then we look at how structures form at the end of the simulation, and this allows us to have something to compare with observations. So just a note for folks who know like sort of redshift, I have snapshots of redshift there, and that just essentially means how far back in time. So the width of the box on the left is about 1/5 of the box on the right, just for reference, but oops, okay. So again, back to the question of how do structures form? This is probably the only plot I'm going to show you from data, but this is sort of like one of the historical figures of from 2009 of getting cosmology constraints from measuring galaxy clusters. So you notice, right, like over time, you get more and more of these like massive blobs, massive halos, where galaxy clusters reside. So what we do in galaxy cluster cosmology, if you have a nice set of observations, as folks back then did, they looked at the sky in the X-ray wavelengths, and they essentially counted the number of galaxy clusters that were further away, so further back in time, because it takes time for light to reach us, and the number of galaxy clusters sooner, right, closer to us. And they essentially quantified the number of halos with mass above some threshold earlier and later. So earlier in time, right, when the universe looked a little bit more smoothish, but then you don't have as many really massive Christmas lights blobs, and later on in time. So early on in time is that blue lower curve with the data points, and then later on in time is the black curve with many more data points, easier to observe things that are closer. And from this, they're able to fit a model that we get from those n-body simulations. They take a bunch of simulations like the one that you just watched and described with your words, and they essentially, they count the stuff in the model. They do this for different cosmologies, so different assumptions of how our universe has evolved and what the contents of our universe might be. They do a fancy interpolation across all of the things that they were able to simulate, because simulations can be quite expensive. And they compare that to the data to figure out, well, what's the closest cosmology model that fits the data? And so that's how they came up with that universe is comprised, in terms of energy density at the present day, has about a quarter of the energy in the form of like mass a quarter of the energy density is in the form of mass, and the bulk rest of it is in the form of that dark energy that leads to the accelerating expansion of our universe. So this is how we constrain cosmology, or try to pin down where in that model parameter space our true universe lies by comparing simulations to what we can observe out in the night sky. So something I want to just point out to you, right? Talking about like, these are really massive objects. How massive are these? All right, you'll notice that the mass in the bottom is essentially showing, when you're counting those halos and the galaxy clusters that live in those halos, you look at them at a given mass, and this is 10 to the 14 to 10 to the 15 times the mass of our sun. So take our sun and just multiply those by 10 to the 14 or 10 to the 15. This is the mass range in which galaxy clusters live. And the way they grow to be that large is through what we call hierarchical structure formation, where little things grow into bigger things, and then the bigger things grow into even bigger things. And at the very tail end of this is when you end up with something like a galaxy cluster. So galaxy clusters take a while to form. They form at the tail end of the history of our universe. And so they're particularly sensitive to that expanding universe at accelerating rate and structures forming due to gravity. So that little cartoon on the right, you can sort of think of time going from bottom to top, where each of those little things forms an intermediate thing, forms a larger thing, forms a galaxy cluster at the end. So the reason galaxy clusters, we like to use them for cosmology to understand what that underlying cosmological model is. What are the contents of our universe? How did our universe evolve? Is because their very formation is really dependent on how much gravity is promoting their growth, right? Gravity leads to structure formation and collapse. And the accelerated expansion of our universe, I really like one of my teachers from a while ago described this as the accelerated expansion of the universe is kind of like an escape velocity. You might have heard of this, that term in one of the previous, business class you might have taken or Saturday morning physics, but escape velocity essentially, right, when you throw a ball up into the air, it comes to a pause and it comes right back down, right? Speeds up as it lands. So if things are dropped from a higher height, don't be near where it lands, right? But if you throw something up into the air with sufficient velocity, it's going to be far enough from the Earth's gravitational pull that it's just going to keep going. You have to throw something really, 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 really fast, so like rocket type stuff, that technology required, right? So galaxy clusters, because of the accelerated expansion of the universe, that acts kind of like an escape velocity, which if matter, like those two like intermediate-sized galaxy clusters are far enough from one another, because of the accelerated expansion of the universe, if they're far enough from one another, they're never going to collide. But if they're close enough to one another, they will grow through that hierarchical merging. So the evolution of galaxy clusters is very sensitive to that balance, particularly later on in time when they're forming. So let's talk now, said a lot about simulations because that's sort of like the land that I mostly live in, but I love talking to observers. They do a lot of cool stuff. We're going to talk about galaxy clusters and observation. I have pulled together a set of 6 images from the Hubble Space Telescope. Some of these 6 are galaxy clusters, and some of them are not. I'm going to set a timer for you to chat with your groups to identify which you think is the most likely galaxy cluster and which you think is the least likely galaxy cluster. And I'm going to want you to come up with some rationale as to why you think it is or isn't. All right, go.
Number 5.
All right, folks. All right, let's come back together. So between 1, 2, 3, 4, 5, and 6, can I hear maybe which one people thought was like highly likely, probably a galaxy cluster? Just, for some reasons, but you can share reasons after. Which one? All right, raise your hand if you think it's 1. Okay, 2. All right, 3. Okay, 4, 5, and 6. All right, I think I saw the most hands up for 5. Okay, what about the least likely? 1. Okay, 2. All right, 3, 4, 5, and 6. Okay, I think maybe 6 and 2. A little hard to tell, but okay, let's take a look at what. Can I hear some rationale for? All right, I remember 5 looked like the most popular one. So for folks who thought it was 5, why? Because it's bright. Okay, I like that. Right, bright, you associate bright with like massive and a lot of stuff, like the Christmas lights at the maximum. Okay, what else? Other things people thought. Why 6?
Clusters of clusters.
Clusters of clusters. There's a lot of stuff there, right? Oh, I see a hand, yeah.
So I think that it's 5 because I see lots of circular shapes that look like galaxies, and they're all right next to each other.
Ooh, all right.
It might just be a zoomed-in version of something.
Oh, fair, right? You could zoom into a really small thing to make it look like it's really big. But yeah, I like that. You had multiple aspects to what you described there, right? You have a lot of circular things that look like galaxies that are very close together, so very clustered, right? Clusters of clusters. Okay, cool. All right. And I think folks said 6 for less likely. Can I hear some reasons for why the less likely? Sorry, say that one more time? The distribution looks a little less like clustery. Okay, cool.
Individual galaxies.
Oh, the shapes of individual galaxies look, yeah. Okay, cool. All right, let's see what these are. Okay, so the actual galaxy clusters are 3 and 5, so people who thought 5 for reasons, yes. And everything else, either just general fields, like I'm going to say the less special fields in the sky, but they're special for other reasons. Not in the same way galaxy clusters are special. One thing I'll point out is 3, you might notice some arcs. We're going to talk a little bit more about that later. So that was like a little bit of a telltale sign for 3 also. I want to go back to the point of like, oh, be really zoomed in. So 2 is a dwarf galaxy. So these are basically some of the like lowest mass objects that we can really, lower mass galaxies that we can see. And so typically, I don't know this exact masses, but they're typically like 10 to the 8th, 10 to the 9 times the mass of our sun, and galaxy clusters are 10 to the 14, 10 to the 15, so orders of magnitude much lower. So what you see, there is a cluster of stuff, but those are like, stars, and we essentially have a zoomed in view of this compared to the galaxy cluster, so that's, dovetails off of like, I wonder if this is just a zoomed in view or not. For that one it is, in terms of like spatial scales. The ones that we can see are closer to us. Okay, fun. I think I have some of like my rationale, which is very similar to what I heard from the audience, right? So one thing that did not come by, just want to highlight, because we will talk about this. So which of the patches I showed you contain galaxy clusters and why? So if you see giant arcs that seem to trace some concentric circles, this is essentially due to an effect known as gravitational lensing. We'll say more about this later. So no expectation that people have picked that out. Also, it's really hard to like squint and see. It's like experts who are like, here are the arcs. Let's like use these to like map out what the underlying mass distribution is. So for 5 and 6, there's, 5 and 3 is the one. So for 5, right, there's more elliptical, spheroidal, featureless shape type galaxies. So the kinds of galaxies that you see in there, the shapes of it. So when a galaxy cluster is building up, galaxies that come into this deep gravitational potential well, it's very hot and it's very dense. We'll see more about that later too, but that sort of shuts off star formation and makes galaxies look a lot like what you see in that image in 5, whereas I think, I asked about 6, and I think I heard right, the galaxy shapes don't look like they belong to galaxy clusters. So if there's more sort of like these spirally arms tend to form stars is probably not interacting with that deep gravitational well of stuff that makes the galaxy cluster a galaxy cluster. And also the crowding, right? A lot of these elliptical galaxies are really close to one another. And one thing that when you look at that crowding of really bright stuff, also there's typically a brightest cluster galaxy, so really, really bright and close to the middle. You'll see a very bright galaxy sort of marking off like, I have grown alongside this galaxy cluster, and I'm part of things that make things very massive and very bright. So yeah, oops, did that one just go off? Maybe if I, oh, it's gone. Oh, there it is. Okay, cool. All right, so yeah. Let's now talk about why we see some of the features we see in these galaxy clusters. All right, so hierarchical structure formation, just going back to that, right? Because what you saw was like underlying discretized mass flowing into one another and forming these more and more massive halos. And in these halos, you sort of map that onto either galaxies if it's a less massive, or a galaxy cluster if it's that big, bright Christmas light in the whole simulation. So galaxies fall in. And we're going to switch to a demo to sort of see what that sort of, oh, is that what that, okay, cool. Looks like in action. So what this is, I'm going to drop multiple either coins, I think there's ball bearings and washers, and you're going to notice that they're orbiting around this funnel, and as they orbit closer and closer, they speed up. So there's, in this, a conservation of angular momentum and energy. Oh, there's a merger. So galaxies, when they merge into galaxy clusters, might merge with one another. I was referring to when the pennies hit each other. And so as material, so galaxies and other stuff, flow in through those filaments to go into those nodes, they come in through the filaments, come in through the nodes. Oh, that one went in really fast. So depending on how they're coming in, that's going to govern their orbit within the galaxy cluster potential well. And things that are sort of closer to the center are going to be moving faster than further away, or if they're coming in with a really fast velocity, in this moment they're going to be really, really fast. And sometimes galaxies fly through and keep going because of that escape velocity. So all sorts of things happen when galaxy clusters are building up through hierarchical structure formation. And depending on which ones we use, right, it's going to have some number of orbits versus not. So this is sort of, I like this as sort of like a schematic to picture like galaxies coming in and accreting into a galaxy cluster. But right as the galaxies are merging in, that's sort of what leads to shutting off some star formation because there's a lot of really actually hot material that they have to pass through when they enter that galaxy cluster potential well. So another thing that we see, I mentioned those arcs. So this visualization of a galaxy cluster, it shows in a shaded region in blue that corresponds to the projected mass distribution that you can infer from gravitational lensing signatures. And what that means is that you have a galaxy cluster, deep potential well, you look at light from stuff further away from it that has to pass through the galaxy cluster potential well to get to our telescopes to take this picture. That light bends. So we're going to move to another demo shortly. But essentially, what happens, right? Distant galaxy, galaxy cluster, the mass of the galaxy cluster warps spacetime, and it acts like a lens the way, like, I don't know if you use glasses, or you've used a magnifying glass, or you just look through a fishbowl, warping the light before it gets to us. So this is a pretty cool, I've never used this demo before, I've seen it done before, but it's pretty awesome. So this is essentially the bottom of like a wine glass type of a thing. So warped glass. So when light's not going through just regular air, but warped glass, it has a different path. And if I place this here, you see that the image of the galaxies gets sort of like extended out or magnified, depending on the properties of the lens, the optical lens. So gravitational lenses do effectively the same thing, just due to gravity. and the gravitational potential. So I'm actually going to try to challenge myself, see if I can make a nice circle here. It might be a little easier with, so you can sort of see that you start to trace out the circular shape of what makes this, like the bottom stand of the wine glass, circular, right? The light warps according to the shape of this glass. And so if I move it here, oh, look, there's a, ooh, oh, almost got it. All right, that's like what an Einstein ring looks like, where you have, if you have the light sources, the galaxies behind the lens, and the relative positioning of those two relative to, us, the telescope, like perfectly matched, you can create a nice Einstein ring circle. Those are pretty cool. Huh, I wasn't sure if I was actually gonna get that. Let's try the small one, just to see how these change. Oh, that was like, I promise I didn't practice that. I'm like, yay, a ring. Cool. Yeah, and then if you have something like a spiral galaxy, ooh, look how much bigger that got, right? So that really bright ring, without that, it's like, okay, I can sort of see that. So some observers use this effect to actually magnify and take a better look at properties of galaxies that are really, really far away to understand things like how galaxies form their stars in the very high redshift universe, so when the universe was very young. It's otherwise very difficult to get this kind of information. So gravitational lensing is also a way we can understand and probe how galaxies even just formed a really long time ago. So this is a really cool effect. What we in sort of galaxy cluster cosmology use this for is a way to map out essentially the shape of this wine glass. It traces the distortions of the background galaxies, map out the mass of the galaxy cluster. And we care about masses because we do that counting game to then figure out how many galaxy clusters exist as a function of mass, as a function of time. All right, that was a demo. All right, okay, cool. So I talked a little bit about how some of those galaxies, when they're coming in, they have to interact with this really deep potential well, and their star formation gets shut off. So I'm going to talk a little bit about how that happens, right? So galaxy clusters, the easiest thing for us to see, because it's in the optical wavelengths, well, for us to visually see and maybe mentally sort of map out, is right, the galaxies, they emit an optical wavelength, so visible light. And they gather together, they come in, coming through those filaments, accreting on, orbiting around. And the thing is, when you have a lot of mass that's collapsing in, you lose a lot of gravitational potential energy. And that energy needs to convert to something else. There's the stars that emit in our optical wavelengths, but there's also this gaseous component that's coming in, hurtling in, and the more that stuff comes in to the potential well, it heats up. So what we have here is we have a conversion of gravitational potential energy, oops, sorry, to heat. It's a conservation of energy thing. So the gas that permeates galaxy clusters, this is called the intra-cluster medium. So intra is like within for the galaxy cluster, and the medium that just permeates it is this really, really hot 1,000,000-degree gas. So right, again, these things are 10 to the 14 to 10 to the 15 times the mass of our sun. So that's a lot of gravitational potential energy that like, there's some conversion going on. You're heating up the gas. And when you have gas that's really hot and energetic, it emits in the X-rays. So this is the same set of wavelengths of like when you hopefully don't have to go to the doctor because you broke a bone and had to get that X-rayed. Same X-rays. And because it's so hot, there's interactions between the galaxies and the intercluster medium that will lead to a tendency for cluster member galaxies to be sort of quenched. Their star formation has sort of stopped because they've interacted with this hot medium. They're like, I can't form stars anymore because I need, gas to cool and collapse into me. So these interactions govern the properties of the individual cluster member galaxies as well. So like looking at sort of those shapes and colors of the galaxies is how you might identify a galaxy cluster. And this is actually one key step in cluster-based cosmology, finding the galaxy clusters in the first place and having some expectation of what the cluster members look like is a way that we're like, all right, we're going to take that as a prior and use that to select out what we think are patches of the sky as galaxies. So essentially exactly what you did by eye, but we have automated ways to do it. Okay, so galaxy clusters emit in the X-ray, very, very energetic. And I just want to sort of throw back to the one historic plot of cluster-based cosmology that I showed you with those data points. Those data points are from the X-ray. They're from the Chandra X-ray observations. So this is NASA's, for more than 2 decades, had been the flagship mission. So collects light from the universe in the X-ray. And then so that's what this purple haze corresponds to. And you'll notice, right, that the purple haze is more intense in the middle than it is towards the outside because there's a lot more hot gas, so higher density, higher temperatures towards the middle as it is towards the outside. So with that in mind, I think this might be the last, yes, I think this is the last chat through with books. So I'm going to ask you to turn to your neighbors, and you can choose both or either one, and try to think through what features in these images might enable a mass estimate. What do you expect to increase or decrease with mass? All right. All right, let's come back together. All right, what about things in the optical? What about the galaxies might give you a mass estimate? Did anyone come up with something?
Gravitational lensing?
Sorry, say that one more time?
Gravitational lensing?
Yeah, lensing, right. So if just as you saw with the with the bottoms of those wine glasses, right? Depending on how those arcs are shaped and how magnified things are, you can start to figure out, well, at least with the wine glasses, right, which one was more narrow and maybe denser versus wider and less dense. And there's an effectively similar mapping to the underlying mass of a galaxy cluster, right? And lensing comes from the background galaxy, so you're going to see that in the optical. Any other things in optical? Not the galaxies. Yeah?
More mass emits more radiation, maybe?
Yes, yeah, more radiation. And what we call that is in terms of number of photons, so luminosity. So more massive stuff is going to have a lot more light emitted. And actually, that's for both optical and X-ray, right? So the more stuff you have, right, because light is a form, radiation is a form of energy. There's energy lost through the photons that get to our telescope. So the more of those we see, the more massive that object probably is going to be. There's that scaling between things like lensing signatures, number of photons. All right, any other thoughts? Yeah?
In optical, you can sort of see the dark spaces a little bit more. Like it's the dark space where light is more present. Yeah, the voids.
Yeah, great. Okay, so looking at the distribution of just how much more dark stuff is there compared to the light stuff, the galaxies. So I'm going to take that a step further, and I'm pretty sure this is one of when I made my own list. Okay, so yeah, gravitational lensing is definitely there from what I'd come up with, and the sort of from the number of photons, luminosity, and just going to the distribution of light spaces and dark spaces. So actually, the number of galaxies, we can use this. This is called the richness of the galaxy cluster. The more cluster members it has, the more massive it probably has, because the more stuff has been hurtling in to build up that dark matter halo over time. And you can map that to also the number of galaxies that we see. All right, I'm going to finish with just sharing some challenges to galaxy clusters, because these are actually observationally quite challenging. So one of the key things is physicists love to make these spherical cow approximations, also with galaxy clusters, but galaxy clusters are not spherical cows. So this is sort of a very nice zoom in from some of my collaborators who made this very high resolution simulation using that dark matter, like discretized mass, run it forward assuming cosmology, and the gravitational interactions. And this is a zoom in on a single dark matter halo with beautiful resolution. And this is not exactly spherical. So that azimuthal spherical symmetry, it does simplify things, but that's not quite what describes this, right? Reality is like, cows like a cow. And physics, we do like to start with something simple. That's a good principle in life in general. Start with a simple thing and then complexify it. So this is not quite mapping to the underlying mass distribution. It is actually closer to that, or a squashed egg. Galaxy clusters are not spherical. They are what we call triaxial. So there's sort of three-ish axes. I think of it as a squashed egg. They fit more a squashed egg definition of a mass distribution if you look at the halo itself. And the problem with this, right, is that when we try to do things like use gravitational lensing to infer the mass, right, we're picking up that squashed egg distribution as opposed to a perfect sphere that we're like, okay, let's like figure out that if this is a perfect sphere, and this is how we expect light to deflect through a perfect sphere, what should it look like? It's not. It's not doing that at all. So, so this is something that leads into what we call like biases in our measurement. Running a little short in time, so we're not going to do a chat through of this, but I'm going to give you like 30 seconds. So here's the squashed egg. And if you're trying to infer mass, either because you're looking at light getting distorted this way, light getting distorted this way, or light getting distorted like straight up and down, these are going to differ, right? So I'm going to give you like 15, 30 seconds to just figure out which one is going to tell you, like, you're going to guess that there's like a lot more mass than there is in a certain direction. Which viewing angle is going to lead you to guess that there's actually more mass, so bias high compared to truth? All right, let's come back together. I see a lot of really great discussions and people visualizing the squashed egg. All right, can you raise your hand if you think that this direction is going to give you a higher bias of mass estimate for direction 1, direction 2, and what about direction 3? So like straight up and down. Okay, I saw a lot of hands for direction 2 and a little bit of direction 3. So here, essentially because this is mass viewed in projection, you want to take your egg, figure out which viewing angle are you. If you like drill a hole through it, you're going to drill through more egg. And that's top to down. Sorry, not top to down. Into the page and out of the page, so this direction 2. It's a little hard to see things because this is in projection for a 3D egg. But essentially, this is your egg. Not that much egg in this direction. Not that much egg in this direction. A whole lot of egg in this direction. So when we view galaxy clusters down its axis, and this tends to be aligned also with that filamentary flow because that drives a little bit of that shape, you get all sorts of biases from that. That's due to what we call projection effects. Oops. Okay, so looking at the egg, you're like, okay, if I drill through, like, this is a 10, 20, 50% for galaxy clusters. So this kind of thing actually is probably a 16 to 22% scatter in the mass. So like up, if you're viewing down that egg direction, or one of the shorter ends, it scatters down. One thing that people say is like, oh, you're viewing galaxy clusters around all angles of the egg, so it should be fine if you're stacking everything, which is okay to a certain extent, but now that we're getting to like very precise cosmology to really narrow down parameter space, we actually need to do better than that. So just to sort of take a look at this, right, the egg was sort of this way in this dark matter only simulation, so it's, if you're viewing it this way versus that way, you get a bias in the galaxy, sorry, the bias goes this way in the galaxy cluster mass, left to right. So that's going to change your estimated number of galaxies and also your estimated mass of a galaxy cluster. And so this cursive projection really affects you trying to figure out the underlying mass to do that number counting game. So if we're counting the number of galaxies, one thing that I will bring up is that, One of the things that is actually going to be a really critical issue with the next stage of experiments that view the night sky is called blending. And essentially, if you look at that previous image, right, if you stare at it for longer or you're going to essentially pick up on the fainter objects, and then it's going to be hard to tell, is that one or two galaxies that I'm picking out. So things like your cluster galaxy membership count is going to change. And also, because you're picking up on fainter things, that's going to mess up your lensing estimates when you're like, how warped are these things? Because it's like, is it warped or is it really two galaxies looking elongated? This affects things such as also your redshift estimates, which is figuring out which things are in the cluster, which things are behind the cluster, and that also messes up your gravitational lensing. And again, if you're looking down that filament, straight down through the long edge of the egg, and there's filaments in that direction, you're going to get more galaxies that are still flowing down the filament that you're going to think belong to the cluster. So all of these things are essentially, these lead to systematics in the measurement that bias your measurement in a certain direction, making it challenging unless you get the modeling right and you're able to sort of either maybe average it out or something along those lines to then map that to a cosmological constraint to understand the history and contents of our universe. So I'm just going to leave you some systematics. This is to say that there's a lot of work that we still need to do to really understand galaxy clusters, how we're measuring them, how they're forming, and then just mapping out the measurements to the simulations, because it's that comparison between theory and data that allows us to really understand models and the reality of like what true cosmology model describes our universe. So there's a ton. That's a takeaway from this. And folks are working in any one of these. Any one of these is like more than a dissertation. It's like several dissertations for someone completing their PhD to start hammering away and chipping away at solving any of these challenges. So I've been thinking about this a little bit more because I'm involved with the Dark Energy Science Collaboration. That means we care about cosmology, which is part of the Vera C. Rubin Observatory's Legacy Survey of Space and Time. So just things that you might want to look up later on. This is a really cool 10-year survey. There's folks working on the first light, testing out the camera down in Chile. And this is going to give us those beautiful images of the sky, particularly of these special fields called galaxy clusters, but also just the southern hemisphere, so half-ish the night sky over 10 years. So that's really exciting. And one of the things we're going to be able to do with that is because it's an optical, we're going to be able to get images of cluster members, their background galaxies, to get those gravitational lensing measurements. So thank you. I'm going to leave you with a photo of my dog. I also hang out at the dog park. This is Choco. She's a half corgi healer. I love her. And so thank you, all of you, for being here, because this isn't possible without you. And I just want to acknowledge, like anything in science, things come together because of a lot of contributions. And there were a handful of folks who really helped with the content of these slides and refinement of just how to think about these things for me. So thank you.
Thanks so much, Camille. When talking to the public, there's 3 E's that we look for. They're very important. One is engaging, entertaining, and educational. And there's actually a 4th, which is exciting. So you've hit all 4 of them. So thanks very much. Great.
Appreciate that.
Great talk. So we're now going to have question and answer period. So people in the audience here, we're going to have microphones. So if you would congregate sort of halfway up the stairs, make your way to the stairway. We'll take a minute to let people who are leaving do that. And we also have questions that have come in online.
Ooh, that's exciting. Yeah.
Yeah. Okay.
Thank you for those demos. I rarely get to play with these ones. So
This is the awkward transition.
Ooh, Okay, so
Oh.
excellent question. That is,
Well, there was-
I want to share it with
oh,
everyone
here.
else because that's an excellent question.
Fell into
Yeah, that is actually one of the ways we probe mass that I
All
didn't
right.
quite get to. So we use spectroscopy, which gives you velocity estimates, and look at that distribution.
We're still working at getting set up here. So let me just start with a question, an online question, which is, where does the you showed one picture of the dark matter distribution, but where does it, in a big cluster, like once it's filamented and so on, where does the dark matter hide? So you can...
Yeah. Where does the dark matter hide? Okay, so dark matter is dark because as far as we've, when I say we, so colleagues who try to do dark matter detections, and they do this wonderful job of like making their instruments as like sensitive as possible, and the hope is that dark matter is weakly interacting enough such that there's going to be some interaction, some particle interaction, that dark matter is then going to interact with itself or something else and emit something that is visible. That has not yet happened. Like, it is a really hard, so dark matter, like thus far, it does not emit any light, right? Things that emit light, like stars, that hot gas in X-ray, us, right? We are visible. Dark matter, to these constraints are not. It's simply something that we infer because of how we see things gravitationally interact. So luminous things, we can look at them in the night sky, and we're like, okay, well, the way that's moving or the way that's distributed seems to imply that there's a lot more mass in that system. And so where the dark matter is, so we can't see it. This is why we have to infer it, which makes it a really cool problem, but hard. And where it's like hiding, it's actually throughout the entire distribution of that galaxy cluster. You probably noticed that there was like a lot more galaxies towards the center for the cluster members, and then it sort of like petered out towards the outside. So we oftentimes say light traces the underlying matter. So there's a lot more dark matter smushed inside, and then it sort of gets a little bit more dispersed and less dense as it goes towards the outer regions. So it's all over that galaxy cluster. Next
Here's a question here.
To me, it's easy to understand how gravity leads to clustering, but not so easy to understand how it leads to filamentous structures. Can you explain?
Ooh, yeah. Okay, so when we think of gravitational collapse, this happens among like 3D axes. So I wish I had sort of a visualization, but if you have sort of relatively homogeneous medium with a little bit of an overdensity, you'll oftentimes end up with this like sort of flat pancaking and then collapse. It all sort of happens in rapid succession. So when things clump together, within those filaments, there's tiny little blobs as well. But I feel like there's a really good analogy to this take sort of like water droplets that sort of attract to one another, right? And you'll get streaks, and not just like little individual droplets. So things want to be close together, but they also kind of want to stay connected to further away things. So that's sort of how you can sort of picture it. That's how the filaments kind of like collapse into one another, but then these really massive things want to also come to one another, so they're going to travel through the filaments. The filaments will also move over time in response to all of these. So things kind of collapse, but you don't get an instantaneous everything just individually collapsing into balls in isolation. They're still connected because the stuff that is in between them also want to stay connected to one another. Does that kind of help? Yeah, it's hard to. I find it like hard to picture unless it happens like a slowdown of the simulation itself. Yeah, happy to chat more and then also to pull up a better visualization at some point. Yeah, next.
Over here.
All right.
What would
Can you come a little closer to the microphone, if you would?
the presence of dark matter change the filamentary structure? Would
Yeah.
it make them thinner? Yeah.
If we reduce the amount of, say, dark matter, right, that's going to change. I mean, we're still going to get something that looks like those like nodes and filaments, and I oftentimes like to think of like, oh, it looks like neurons in the brain. That's sort of like the way like hexagons are a common thing in nature to like optimize shape. You're still going to get that kind of like collapsing and trying to stick together. but the statistical descriptors of how we see visible matter through like the filaments and the halos are going to change if we say tune down the relative amount of dark matter in our simulation, right? I think earlier on I mentioned we assume gravity, we assume some cosmological model, which includes how much matter are we going to put in there, dark matter or baryons. And certainly as we change that, it will, depending on how much we change it, won't necessarily look obvious to the human eye, but what we can do is we could do statistical measurements in the simulation, like count the number of halos, measure their masses, or look at how closely distributed they are. There's a way to measure clustering, basically look at how close things are together on different scales to measure how clustered they are. That clustering statistic will also change. So it'll change the statistics of how the structure is distributed.
There's 2 online questions I'm going to try to put together a little bit. So I'll read one. From a layman's point of view, galaxy clusters appear to be self-organizing structures. How is this explained with respect to entropy and disorder in the universe? And so there's questions about entropy, basically.
Yeah, no, that's a good question. Okay, so let's see. So galaxy clusters, right, so the idea of entropy is essentially unless you put energy into a system is going to lead towards disorder. So essentially, right, like if you toss a deck of cards out, it's going to just get really awfully shuffled unless you put your own energy into ordering them aces through king or whatever, right? And with galaxy clusters, I guess the ordering energies that govern how they are distributed, there's gravity, right? There's an energy conversion going on there. And then because if we didn't have something like dark energy leading to pulling things apart, things would just collapse and collapse and collapse and collapse, and you wouldn't see the same patterns. So certainly, if you take a look at the gas, right, so your entropy is also related to your temperature and your density. One of the things that also happens within galaxy clusters, this is more galaxy formation within the clusters and just galaxies in general that I didn't get a chance to talk about, is that gas cools and then forms stars. So as you cool, right, you emit photons. That's how you sort of lose the energy, and then that goes out into the universe. If you think of the entropy, just it's out, and then there's sort of the leftover formation of stars that then form into the galaxies that we see in the galaxy clusters. There's a lot of that goes on in the galaxy, but both structure formation in galaxies that you could relate to the thermodynamics, but that's maybe some smatterings of it. Quite, yeah.
In smaller things that cluster together, I'm used to the idea of there being significant angular momentum. Do galaxy clusters have angular momentum as one of their?
Oh yeah, yeah. Galaxy clusters absolutely do have the angular momentum. So that's something that you would consider when right, you have potential member galaxies that are feeding in through the filaments. And so this is what we say is no longer there, but the yellow funnel, when they come in, right, they have some orbit, and then over time, they also lose energy through dynamical friction as they're merging in. And this is also how that brightest cluster galaxy might build up its mass with some of those mergers, merging galaxies coming in. There's angular momentum in the entire system, so it is sort of roughly rotating in some coherent fashion. And then through some energy losses, you're going to end up with mergers within the cluster as well. Yep.
So here's a question back to the X-ray versus optical images. Why are they different?
Okay, so I can actually, let me go back to that. Hopefully this will, turn that back on.
And also maybe how are they the same?
Yeah. So this is that left versus right, and is this no longer? Oh, there it is. Okay.
5:30-ish.
So just so folks remember what that looks like. Okay.
Yeah,
so
it was
left
30.
versus right. This is the same galaxy cluster. So the images, the way folks put this together, I think is really clever. They essentially color map what they see from different telescopes. So the optical, so right, you have the same galaxies. I think just essentially the way they rendered each one, it's from the same observations. It just ended up a little bit brighter on the right side and a little more saturated. But that blue haze on the left is because they made some measurements to infer the underlying projected mass distribution. And it's like, okay, where it seems like there's a lot more mass, sort of like maybe down that egg, we're going to color that with a corresponding brighter blue versus less. And then with the X-ray, we're going to color code that according to how many X-ray photons we're picking up in each pixel, and overlay that on top of what we get from just the image of the galaxies. So it's, I think it's a really clever way to actually put things on top of one another so you can sort of see the correspondence between, like, there's more galaxies in the middle, there's more mass in there, and there's more hot stuff emitting more photons in the X-ray. That's why they look different. I hope that's what the online question was getting at. Yeah.
X-rays take the temperature.
And X-rays, yes, that's right. So from the X-ray, you could take all those photons, create a spectrum, so plot the number of photons as a function of energy, and the hotter it is, you'll have more high energy stuff when you look at the number of stuff at high energy, number of photons at high energy. And when it's higher density, you simply end up with more, so that brings the normalization of your count of photons up and down. And so if you look at the stuff outside, it's a little cooler, so you have more photons at lower energy.
Over here?
Yeah, I have a question and then a follow-up question.
Yeah.
So, thank you. Is there like an explanation or theory of why it's a like a smushed egg shape instead of a smushed sphere, just like a sphere shape?
Why is it more like egg-like than sphere-like?
Yeah.
Sure. So a big part of that is because it's the way the structures are forming. You have those, maybe I'll go to the filaments. You'll notice the way the galaxy cluster is getting, fed more material is not like this, isotropic, spherically symmetric feeding. It's preferentially through those filamentary material, and that is what leads into that elongation, because you're going to, at some given point in time, just have a little bit more over here, and that material is going to fly in and make some rotation. It's just not being fed in a way that you have an even amount of stuff from every single direction. Yeah.
And then, so as for the smushed egg thing, so that could be maybe due to the like the rotation of the matter coming in. Has it possibly been theorized that it's like a spinning of the fabric of space-time that is like flattening the egg out?
Oh, spinning of the fabric.
I don't know. I was just having like an image in my head of like that grid like spinning, the grid of the fabric of space-time spinning in order to flatten the egg out. Maybe, I don't know.
I like that you have so certainly everything with mass is like imprinting itself in the fabric of space-time. I don't quite have a good visualization of the spinning of it, but
yeah,
I like how you're mapping that into that.
In my head.
Yeah. No, you definitely want to sort of like, no, that's a cool mapping to have of the imprints and anytime you have mass, but cool. Yeah.
So this goes back to the formation of the filament structure.
Sorry, which structure? The
filaments.
Oh, for the filaments, yeah.
I seem to remember reading about or something about magnetic fields.
Yeah.
Could that be magnetic field lines that the filaments are forming along? Or is that, that's just one idea.
Yeah, so magnetic field lines, okay, so anytime you have motion of charged particles, so if you have essentially, like electrons, when you have a really hot ionized gas, you're going to separate out your charges. So you have now this hot plasma that's charged, and when you have moving charges, that generates a magnetic field. I don't know if anyone's like played around with like a current and then just interacted with magnets. So certainly there are magnetic field lines that get generated in these systems. They're often not quite coherent. Some of the more like coherent shape type things that we might see. I remember someone mentioned black holes as like a fun universe interest, right? When black holes are creating hot material, that's also like very hot ionized material. You create some magnetic field lines and you have this collimated jets. That's not quite what's going on with the filaments. But just to point to that, you do have some astrophysical phenomenon that'll do this kind of collimation with a coherent magnetic field structure. And there's thoughts that there's some bits of that, but it's different for the filaments itself. Yeah, that's a good question because yeah, that's definitely fun stuff that's going on. Yep.
Following up on that a little bit, maybe in a way, sort of more exotic, is gravity the only force that matters? Was the question, and what about dark energy?
Yeah. So dark energy is super important in how structure forms. And essentially, we don't know exactly what it is. This is, so you might notice, like, dark matter. This is this non-luminous thing. We don't know exactly what this is, but we know it interacts gravitationally. And dark energy, what its characteristic thing is that it leads to the expansion of our universe. So essentially, if things are some distance apart, I had this really great. So if you take a balloon and you draw little fake galaxies on it, the surface of the balloon, and you blow the balloon up, that's essentially what dark energy is doing. So going back to dark energy, what happens there is that dark energy is what suppresses that collapse of structure. So far into the future, things that, well, Andromeda is our nearest galaxy, that's going to merge in with us because it's close enough, but further things that are further away are going to be too far to actually eventually collapse in. So that is an important component of structure formation.
Hey there. So going back and remembering picture 5 of your galaxy clusters.
Yeah.
When you're analyzing a picture like that, you had said one of the hard things to do is figure out what's in it and what's out of it. And
oh, yeah.
So how long does it take you to analyze a picture like that to figure out, is this a cluster and what's in it and what's out of it? And what kind of tools do you use to like figure out the redshifts of every single little thing in that to know what's in it and what's out of it?
Yeah, that's a great question. Okay, so maybe I'll try to go back to that for one of them. Okay, let's just take this, right? Let's take this example galaxy cluster, which there's a bunch of galaxies in this field, in this snapshot, some of which belong to the galaxy cluster and some of which do not. So what we will do is we will essentially, we have this image, but we actually have it oftentimes in multiple bands. So we're essentially taking this picture in different colors, so different wavelengths. So LSST, it will be taking in 5 different bands within the optical. And so the first thing is to find all of the objects. So you could do sort of a peak finding method. Be like, where are all the brightest stuff? Here's an object, and here's an object. And this is where that effect of blending can become problematic because you're not properly separating out individual objects. And then you try to get all the light from the individual objects and use that to essentially characterize those individual galaxies. If you have the 5 bands, this is sort of sampling an energy spectrum, just very coarsely, of the light coming from these galaxies. And that's how we can figure out, well, depending on the kind of galaxy it is, if it's star forming, it's going to be a certain color. If it's quenched, it's going to be a certain color. That's part of how we figure out, is this likely belonging to the galaxy cluster? But then how far, like if it's outside the galaxy cluster and way, way behind or not as far behind, that's going to depend on the pattern in those 5 bands. So we call that redshift estimation. So there are folks who, there's actually a bunch of methods to do redshift estimation off of that, some of which uses neural networks, deep learning, sort of an AI application. Some people use AI to do the galaxy cluster finding as well, like you use a deep neural network to just learn patterns that we are not necessarily verbalizing or able to identify, or you can explicitly code up something like find a bunch of galaxies that are fairly red and within some distance of one another in the sky. So these are the series of things that we might do to try to do all that teasing out and then measurements and then propagate downward. And eventually get a mass and a count, and then cosmology, yeah.
Just curious.
Yeah.
Recently, there's been news that they've looked very far back and found stars and galaxies that are not much different than we're seeing more contemporary. Are there also galaxy clusters as they look way back?
That's a really great question. Yeah, so you're possibly talking about some of the JWST measurements, which is one of the more recent launches, maybe 2 years ago. But yeah, and it gives us a really nice window to earlier on in the universe. So the question was, are there galaxy clusters that far back because they're finding galaxies that far back? And the answer is we don't see galaxy clusters that early on, so far away means earlier on in time, because again, it takes light time to get from when that object emitted that light to us. So the further away it is, we're taking a snapshot of the earlier, younger universe. So, right, galaxy clusters form hierarchically. So that far back in time, there's been really small stuff that merged into some intermediate stuff, but we haven't had a long enough universe for that intermediate stuff to create the most massive stuff. So this is why galaxy clusters are very special, because they're very massive. They map out what happened at that tail, later on, closer to our present day of time. And this actually happens to be the period of time when dark energy kind of dominates. So if we really want to sort of tease out dark energy and its role in structure formation, this is one of the roles that clusters can help play. But yeah, earlier on in time, there's really cool, how do galaxies actually form? Because topic for another another one, but essentially, yeah, the universe has it was opaque and then gets reionized through the first light from all of these things, and those are the things that are different questions, but really awesome stuff that folks who are looking far back in time are able to answer, or more able to answer now.
So this online question is from Arcana Dialu. And the question is, how do you constrain or maybe calculate gravitational escape velocity? And how do the biases impact those estimates?
Gravitational.
Escape velocity, yeah.
Escape. So for, in galaxy clusters, I guess this is maybe referring to some galaxies might hurtle in through and then keep going. We call these flyby galaxies. They don't end up members of the galaxy cluster. So you could do an energy budget estimate of balancing out essentially if the gravitational potential energy of the galaxy cluster and how much energy something hurtling in loses if that starts to eat away enough at the kinetic energy that that object has. So you can essentially do an energy budget thing to figure out, but typically what we do is we actually have simulations that just self-consistently track the evolution of individual simulated galaxies building up a galaxy cluster that's simulated. And we see that some of these fly by versus not, and then if you do the energy calculation, it would correspond to that as well, because it's self-consistently calculating all of these values.
Okay, a couple more questions, I think. So here.
Yeah, so talking about perspective biases, is redshifting the primary way you differentiate those harder to see galaxies?
Oh, sorry, harder to see from blending or things that are really faint, or?
Yeah, from things that might be behind it or may not be part of the cluster. Is redshifting?
Oh yeah, yes. Yes, so identifying the redshift of a galaxy is one of the primary ways we know that whether it's a cluster galaxy member, or we call these source galaxies because they're the source of light that get lensed. So yeah, redshift's the primary way because they're further behind. And so oftentimes, so not just for galaxy clusters, but people will do this for also, there's this term called the cosmic lensing. So things, we have mass all over our universe, and we can use galaxies at any distance and try to statistically quantify how much they get deflected, which traces out how much mass is between that galaxy at some distance away and us. And as you do this further and further back in time, that's another way we can probe the structure of our universe. But yes, redshift's a key way. Mm-hmm.
And our last question.
So you've kind of mentioned the competing effect between gravitational collapse, which brings galaxy clusters together, versus dark energy, which is kind of expanding space and pushing stuff out.
Yep.
And then in another one of the plots, you show the curves of the distribution of the galaxy clusters and how that's increasing over time.
Yeah.
So does that mean that gravitational collapse is winning that competition? like it's like things are pulling together faster than they are expanding?
That is a really good question. I used to have like a slide for a different talk that I would give where it's like dark energy and dark matter like in competition. It's like these two like mice boxing each other. But so dark matter actually had been winning for the majority of the history of our universe, and most recently it's actually dark energy. And when I say winning, it's when we, the plot that you're describing with like the number counts, if we look at the inferred energy density, so right, mass is a form of energy, so you could translate the energy in the form of mass into an energy density of our universe. Right now, the energy density of dark energy is actually the dominant one. But things had been forming, which is why dark matter was winning for a while. And that's how things had formed. And things are still close enough to continue forming, but because dark energy is now winning, there's some stuff far away from each other that are never gonna get to meet. Yeah, great, thanks.
Okay, well, that was it. So thanks so much again, Camille.